Good afternoon, this is Schweitzer, and we're going to give you the answers to our preliminary quiz on stoichiometry. The two main topics for this thing are going to be using mass and other things in stoichiometry, and also solutions. Alright, so methane reacts with oxygen to produce carbon dioxide and water. Write out the balanced equation. I'm going to put it right here. So we'll have CH4 is methane plus, and again, the main goal here is to try a problem, then check your answer. CO2 plus H2O. If you're into the stoichiometry like you should be, you should realize the balancing is critical here. One carbon, 4 hydrogens. I need a 2 here, and 2 and CO2 here. So there's 4 oxygens, and I'd like to put a number right here to balance it at 2, and have does work. So 1, 2, 1, 2. Initial stoic ratio, and that's always something that I'm looking to use ice table. Now remember, we cannot have grams in this thing. All right, I have 25 grams of methane, 25 grams of O2. So as far as limiting goes, looks like oxygen used up at a greater rate, but the equal masses, I can't really compare these unless I'm in moles. Depending on how good you are, but that's what we typically want to do. So 25 grams of the methane, 25 grams of the oxygen. The methane is going to be 1, get rid of grams and go to moles. 1 mole is 16 grams. So I have more than 1 mole, not quite 2. Dot line, get rid of grams and go to moles. 1 mole is equivalent to 32 grams. So I have less than 1 mole, and I'm using it faster. Right. I immediately in my mind, this is my limiting reactant. I will keep going here. 25 divided by 32 for the exact answer. 25 divided by 32 is 0.78, and then 25 divided by 16 is 1.56. Now I'm in moles. I can clearly see how many I have. Plug the numbers in here, and I have 1.56. I have 0.78. This is in fact my limiting reactant, less of it and higher rate used, minus 0.78 to 0. And I need to jump from here to here. And you should be showing your work, even if it's simple, 0.78 at used this guy. So it is at a 1 O2 to 2. See, this is O2, so the 2, common mistake, has to go here. 2 to 1. And this is going to be CH4. So divide it in half. 0.39. Make sure you put that number right here so I know that work is associated with it. So it's going to be minus 0.39, and subtract those things. And I have 1.17 in excess. So it's a positive 1.17 moles of excess. I will at that point be gaining 0.39 here, and I will be gaining 0.78 here. Alright, that being said, all my moles are done. So it says ice table, determine moles of each reactant left after the reaction is ended. So that's all moles. Alright, convert the moles of carbon dioxide to liters of at given conditions. Okay, it's 1 atmosphere, 25 degrees Celsius. So this is not at STP. So you cannot use the 22 to 1. You have to use PIV. PV equals nRT, and I want to solve for liters. nRT over P. N is going to be, for the carbon dioxide, is 0.39. R is 0.0821. The temperature is 298. That is gonna, so 273 is standard, so we want 298 here. plus 273 equals 298. That's where I got that from. Divided by the pressure, which is 1 atmosphere, which is 1. All right. 0.39 times 0.0821 times 298 divided by 1 equals 9.54. 9.54. And that'd be liters. It would be close if you use the 22.4 to 1 because it's not that far off, but would be something that would cost you work-wise. All right, convert moles of water to mass. Look at that guy. So 0.78 moles. Dot line, get rid of moles, and go to grams. 1 mole is equal to 18 grams. Where'd that come from? Well, H2O, this is 1 times 2, and this is 16. Add those together, and I get 18 grams per mole. That's how much 1 mole weighs. I have 0.78 moles, so I'm not going to get 18. Less than 18. 3/4 of 18. 0.78 times 18 equals 14.4, and that's about that. 14.4 grams. Convert excess reactant to particles. Okay, so that's this guy. We have 1.17 moles, and those happen to be molecules. So a particle can be lots of things. Molecules could be atoms, could be ions. So, but this is a mole. All right. So to get rid of moles and go to molecules, or just label it particles. Molecules. 1 mole. Here's the only place I use this number: 6.022 e to the 23rd equals. Now I have more than that, so all I got to do is take 6.022 times 1.17 equals 7.04. So that gave me 7.04, 7.04, and I just keep my e to the 23rd. All right. Draw a representational picture of this after completion. So I have essentially this is what I want at the end is what I want. I want, well, for every 2 waters, I want 1 carbon dioxide. Looks like I have a few more the methanes as well. So I might draw 2, 1, and 3. That might be good enough. Or 2, 1, and 4. For sure want to make sure that my waters are twice my carbon dioxides, because that is happening stoichiometrically, always comes in that ratio. And I'll just put CH4 as my excess. There's quite a bit left, so I'm going to draw 3 of them. I have more of the methane than I do the water. So, all right, number 7. Draw a graph representing the relative concentration as the reaction proceeds to an end. Okay, so in this case, we start out with 0 of the carbon dioxide. We start with 0 of the water, and we start out with a certain amount of. We start out with more of the methane and less of the oxygen. All right, so the way this works is like this. Let's just say, like here would be the O2, and we'll call this the methane. Okay, now the oxygen is going to get eliminated the fastest. It's being consumed twice as fast as the methane. So I'm going to drop this guy down right here. Okay, it's 0. This is where the reaction stops. All right, this guy would be not as steep because it's not being consumed as fast. The carbon dioxide is produced slower than the water, so I might draw this guy like that for the CO2. And the water is produced twice as fast as that, a little steeper. And at that point, that might be a decent. This would be water. Notice that this whole length is twice this. I have more methane left than I start than the water. So either way, it doesn't be perfect. That's about right. And this guy is at 0. So another example of just things being consumed, losing some things, gaining other things. I don't think as of doing this video, we haven't done an example like this yet, but should make sense. Okay. All right, and stop there. Thank you.